Login accepted.
Yes, there are people there. It's quite hard to see when you're on stage, the light's on. How's everyone's second day been? Thumbs up, thumbs down, thumbs up. Awesome. We're coming to the end, so thank you for sticking with it. So my name's James Lewis. Hello. I'm going to be talking about a bunch of things that have been on my mind the last few years, but I wanted to start with this quote, or paraphrasing a British science fiction author, Charlie Stross. It's the only AI in this, so if you come expecting LLMs, RAG and various other things, you'll be disappointed. He says, artificial general intelligence is already here. We call them companies, and we get paid to execute their algorithms very slowly. And really that's what this talk is about. It's about the organizations in which we work, the systems that we build within those organizations that we call teams, and the way we go about delivering software these days. So a bunch of techniques, ideas for improving the flow of work through our teams, through our organizations. So it's called How Flow Works, but it's also, because it's me, got a bunch of other stuff in here because I can never keep my mind on one thing. I think it's a kind of ADHD type thing. It's like shiny stuff. So a bunch of other stuff as well, other curiosities. So what are those other curiosities? Well, I'm going to cover off the surprisingly recent invention of all the things, why AWS, or insert your favorite cloud provider, and self-service ate your lunch. I'll ask the question, are we engineers now? Real engineers? Talk a bit about phase transitions in oligarchic societies, because everyone likes a bit of economics at 5 o'clock in the evening, don't they? Why traveling slower counterintuitively makes you go faster. Why you should never sit next to the Cassandra admins. And what Lego has learnt and can teach us about batch sizes. So that's what I'll be talking about. Oh, and this idea of flow and how flow works. If you don't know who I am, just very, very briefly, my name's James. I work for this company called ThoughtWorks. We're a global consultancy that build bespoke software for people and do everything from strategy through to infrastructure, etc. Platform engineering. I'm most well known as one of the grumpy uncles of microservices. So back in 2014, would you believe 10 years ago, Martin Fowler and myself wrote the original definition of microservices, which you can still find on Martin's site. And myself, along with Adrian Cockcroft and Fred George, I guess we're the sort of originators of that idea. More recently, I've been writing on how to displace legacy code, so patterns of legacy displacement, with two of my other colleagues, Ian and Rob. And this is trying to answer the question, when people talk about displacing legacy, everyone always says you use the strangler vine pattern. Just strangle it, strangler vine. But what does that actually mean? What are the actual patterns you can use in order to either strangle or otherwise displace legacy systems? So take a look. It's a work in progress. Apparently we're writing a book. I didn't know this until Martin Fowler announced it on Dave Farley's continuous delivery channel. Anyway, so that's me very briefly. So I'm going to start off with just taking a little recap of a bunch of technologies, techniques that have helped us improve flow, the flow of work, the flow of value in our organizations. And when I talk about flow, what I mean is how information flows, how work flows, the invisible stuff that we work with every day as technologists. So from ideas through a series of activities, value-adding activities, flowing through into working software in production. That's what I mean by flow. I'll be going into a bit of detail what I mean about value-adding activities and this kind of stuff as I go through. But let's start with a quick recap. Life moves pretty fast. If you don't stop and look around once in a while, you could miss it. Anyone know where that's from? Bueller? Ferris Bueller's Day Out, whatever. God, you really are tired, aren't you, the lot of you? Or you're all young. Maybe that's what it is. Maybe you're all just young. So I've been a part of ThoughtWorks. I've been in ThoughtWorks since 2005, about 18 years. And about 2010-11, I became a member of what we call our Technology Advisory Board. And the Technology Advisory Board is the group that puts together something called the ThoughtWorks Tech Radar, which you might have come across. If you haven't, it's quite interesting. It's like a look at current bleeding-edge technologies that our teams are using around the world. And I thought it'd be interesting just to take a little look back at when some of the things that we take for granted first appeared, right? First appeared in our conscious. So Android, just to set the scene, Android first appeared about 2010 on our tech radar. We then had distributed version control about the same time. Before that, of course, it was, well, SVN if you were lucky, Perforce if you weren't. Before that, SCSS, CVS, etc., etc. But then distributed version control is, of course, something that's absolutely taken the world by storm. We can't write software these days without reference to GitHub and to Git. And it's unfortunate because I personally think Mercurial was the better tool, but never mind. Just after that, we started talking about AWS. We were using AWS a lot in anger, so we put it on the radar. And, you know, it's kind of interesting, right? Because back in 2011, when we were all very much data center focused, most of the big organizations, you know, they would never think about using like utility computing or cloud computing. It was such a new idea. You know, who would have thought that, you know, 15 years on or whatever it is now, 20 years after AWS, I guess, started, who'd have thought it would have been a thing? Now, I was actually the fourth, in fact, AWS trainer globally. Back in 2011, ThoughtWorks was asked by Amazon whether we would run their training for them because they didn't want to do it themselves. And this was from one of the original slides from that training course back in 2011. Those were the services at the time that AWS were offering. Who'd have thought AWS would be a thing? Why is AWS a thing? Why is it that AWS has sort of taken the world by storm? I like this little cartoon. This is like, you know, your boss is reading Computer Weekly or he's reading the Register online or something, and he says, "Oh, I've heard about this thing called a platform. Apparently, we get a Devoxx with it. We must have one of those." And you sort of go, "Okay, yeah, sure, why not?" But why is AWS taking over? Why does everyone use the cloud these days? And it's because of queuing theory, I think. I think this is the reason AWS took over. Infrastructure as a service platforms, they are MMC queues where C tends to infinity. I'll explain a little bit about what that means in a moment, but just keep that in the back of your mind. So we had AWS about then. Shortly afterwards, continuous delivery first appeared. The book was published back in 2012 by two of my former colleagues, Jez Humble and Dave Farley, based on the work mainly we were doing in London at the time, in lots of our different clients. And continuous delivery was really the first, it was the first time that patterns like blue-green deployment or canary releasing were talked about or described. It was the first time that build pipelines were talked about. And these are all obviously concepts now that we rely on daily, right? I mean, I'm not sure if there's probably anyone in the room who doesn't have a build pipeline automatically compiling, testing, and then deploying their code. But this is where it came from. It's a pretty recent idea, continuous delivery. Continuous integration was a little bit previous to that, the decade before, but continuous delivery itself only came about in 2012. After that, we had microservices, first appeared in 2012, I think the second half of 2012. Interestingly, it was on our radar. We were using the technique globally before we actually defined what it was, which is a strange conundrum. The other interesting thing about microservices, it's never made it into the adopt ring of the ThoughtWorks radar, because we always felt it was too nuanced a decision as to whether to use microservices or go with something like a well-structured monolith. I have to say that's contractually obligated because Simon Brown is sitting over there. And again, microservices in large part, you know, whilst microservices, yes, it's about splitting things up into smaller bits and single responsibility and all that stuff, a lot of the reasoning behind microservices was about going faster. How can we get more stuff done more effectively, right? How can we separate our components out so that more people can work on them in parallel? How can we do that? That was a lot of the early thinking behind microservices. We then had Docker appear back 2014. Would you believe Docker is only that old? It's only been around about a decade as well. Of course, containerization has now eaten everything. After that, we had Kubernetes first appeared. I need to put the S in, but Kubernetes was around 2015 as well. And pretty much, I imagine, I won't ask you to put your hands up again because everyone's too tired, clearly. But I'm sure there's a lot of people in the room who are using this on a day-to-day basis. It's become containerization, and using Kubernetes or other orchestration tools has become the default way we deploy software, using continuous delivery via build pipelines, often with microservices. So after that, we had a whole bunch of other stuff. Platform engineering teams came next. Now, that's the joke about the platform thing. The thing with platform engineering teams is we put this up there as this idea of, hey, you can build a team that's going to provide access to tooling so that you don't have to build it yourself. And then over the course of about another 3 or 4 or even 5 volumes of the radar, we had to keep saying, no, not like that, like this. So we had things like product thinking for platform engineering, for example. So actually treating your platform as a product and having product ownership rather than just doing a build it and they'll come approach. Because what we were starting to see, and this is one of my colleagues called this the half-assed private cloud. What we were starting to see is organizations saying, hey, we're going to have our own clouds to make us go faster, and what we're going to do is just put an API over the operations team. Right? This is my colleague Evan Botcher that wrote this up. We'll just put this API over an operations team, and we'll call it a private cloud, or we'll call it a platform, and we'll be done. Right? Or you have a nice pointy-click way of essentially creating a ticket that goes into a ServiceNow queue and nothing actually changes. You know you've got one of these, and one of the symptoms or signals of one of these is if before you had the half-assed or superficial private cloud, it would take 3 months to get a database. Now you've got a nice point-and-clicky way of doing it, but it still takes 3 months. So we had to keep saying, no, not like that, like this, not like that, like this. I'll come on to that in a moment. The second part of this cartoon is, 2 years after your boss has asked you for a platform, you go, okay, we've implemented a DevOps now, we've got this platform, but actually we still can't get anything done because things still take a long time. I did mention, or I promised I'd explain that comment about MMC queues. So I'm going to give you a quick recap on queuing theory now, because I think queuing theory is at the heart of everything we do when we think about improving the flow of value, whether that's by deploying software, whether that's writing software, etc., defining software, and so on. So this is a queue. And in queuing theory, you have a couple of different ideas. You have producers pushing stuff into a queue, so normally messages into a queue, and that's called arrivals. Then you have a number of service nodes, which read messages off the queue, and then you have departures from the queue, depending on the rate at which you're able to process messages. And in terms of queuing theory, depending on the number of service nodes, that's the C bit in MMC. So you have different types. You have an MM1 queue, where you have a single service node. So this is if you go to the supermarket and you've got your groceries and you go to the checkout, right, and the person at the checkout is scanning your groceries, that's an MM1 queue because there's one single person doing that. If you've then implemented, say, competing consumers in a messaging system, Rabbit, insert your flavor of N queue, you have what's called an MMC queue, where C is the number of competing consumers that you have taking messages off the queue. So C is the number of service nodes. And we can think about infrastructure and platform engineering via this idea of queue theory. Because when you have a traditional ops team, essentially what you have is a queue in front of a bunch of people, right? So if you want a database, you want a VM, whatever it is, you've got to create a ServiceNow ticket or whatever that ticket is, or whatever system you're using, and you have a bunch of these building up in a queue, and the rate at which you can process these requests for new hardware or whatever it is, for provisioning something, is proportional to the number of people you've got in the ops team. The problem with this is obviously they're expensive, they're skilled, so there's a limit on how many you can hire. So essentially, what we have here is an MMC queue where C is the number of people that you're able to hire into your ops team. You then have this half-assed or superficial private cloud, as I mentioned, where what you do is you basically put an API over your traditional ops team, or you automate putting tickets into the queue for them. You still have an MMC queue where C is the number of people. The rate at which you can process requests for new hardware or provisioning stuff is proportional to the number of people that you have. But then you have infrastructure as a service, and this is where self-service ate everyone else's lunch. So the cloud providers ate everyone else's lunches. Because with self-service infrastructure, right, the rate at which you can process requests for new infrastructure, the rate at which you can provision stuff is only limited by the hardware that you've got running your hypervisors, essentially, the control plane and the data plane, the hypervisors. So essentially you've got an MMC queue where C is tending to infinity, or in fact C is tending to the limit of the hardware that you've got, which is why it's so fast. And this is why self-service infrastructure was probably the most, along with continuous delivery, was one of the most important steps that we've made in terms of improving flow. It's also, unfortunately, one of the things that we don't necessarily think about. And we think, oh, we'll put a platform team on top of that. And then we have what we come across quite regularly now is half-assed platform teams, where we put basically a bunch of people in front of your self-service infrastructure. And now you're again limited by the people you can hire in the platform team and their ability to keep up with requests from the teams that they're delivering software for. So essentially, we've got these different team shapes for kind of ops and the interface between provisioning and infrastructure and so on. You've got traditional, you've got this half-assed private cloud, infrastructure as a service, and half-assed platforms. And three of these are expensive and slow and impede flow, actively impede flow, because you're rate limiting essentially your ability to provision and deploy software based on the number of people that you've got. Whereas infrastructure as a service, but in particular self-service infrastructure, this is why AWS is a thing, and it's so important I'm going to put a box around it and I'm going to flash it at you. So that's why AWS ate your lunch. Shortly after we put platform engineering teams, we then had data mesh. So data mesh, in my mind, is kind of like applying microservices principles to data, to the last realm of tiered architecture, which is data. And then after that, we had a whole bunch of other stuff, mainly about data, and then lots about machine learning. And I think the last radar was about 35% large language models, vector stores, RAG implementations, and so on. But I'm not going to talk about that. So that's a brief overview of where we've come from, the different sort of things that we've discovered over the last sort of couple of decades that help us get stuff done, different techniques, different patterns and principles. So how do we think about building systems optimizing for flow these days then? What are, in my opinion, the canonical ways of looking at this, or the canonical tech that describe it? So I've mentioned continuous delivery already, so continuous delivery, where all these different patterns came from. Building microservices. Now I put this up, Sam Newman's brilliant book, and here's a like behind the curtain quote for you from Martin Fowler, which was that him and myself were going to write a book about microservices until Sam published this, and then Martin said, let's not bother because Sam's is annoyingly good. So we thought, okay, we won't bother. But building microservices, it's not just about microservices, it's about modern software engineering, right? It's about how we test software, it's about how we deploy software, how we version software, how we think about splitting things up. Again, how we optimize these systems to get stuff done. It's building microservices. The next one I'll call out is building evolutionary architectures. Because whilst we've got build pipelines, we've shifted left on lots of different things, security, testing, and so on, there's a bunch of stuff that really impedes flow that we still have to sort of go through in many regulated, say, environments or whatever. So things like audit, compliance. How do you guide the evolution of your architecture via principles? And building evolutionary architectures introduces this idea of fitness functions, and you can implement fitness functions in an automated way and run them as part of your build. And of course, with things like Open Policy Agent now as well, we can start to shift left on things like controls around how we're building software as well. Again, helping us improve flow. Now, one of the things in the State of DevOps reports that came out was when you have change request boards or architecture review boards, when you put essentially a blocker in the way of work flowing through the system, if you've got those things, it predicts that you're in the low performing cohort of organizations. It predicts, and I'm using that deliberately, it predicts that you're in the low performing cohort. And it's because you're putting blockers in the way of flow, of the flow of ideas, of the flow of work. So shifting left on these things, super, super useful. But then I want to call out the daddy of these books, the Principles of Product Development Flow. If you haven't come across this, this is one of the best books about maybe if not the best book about the economics of why what we do these days in terms of building software in a lean or agile way, why that makes sense, why that works. And I'll come to a bit more about this later. We then got Accelerate. I mentioned Accelerate already. The reason, personally, I think this is so important is because it's peer-reviewed. It's actual science based on data. So the conclusions from it, which sort of show that using things like continuous delivery, using things like servant leadership, building organizations that are adaptive and learning organizations, they actually do have an impact on your bottom line. It's not just a bunch of hippies in ThoughtWorks telling you it's a good idea. And then Team Topologies. And I love this book. This has almost immediately become canon. Matt Skelton, Manuel Pais, describing the different team shapes you can use for optimizing flow. And there's two reasons I like this book. The first one is because, like domain-driven design gave us the idea of ubiquitous language for our businesses, this gives us the idea of a ubiquitous language for our team shape, so we can use the same words and mean the same thing when we talk to each other about them. But it also talks about cognitive load. How should you structure your software? How you should break up your software? How the teams that are assigned to those software, how much they can take on in terms of building working software. So we've got a bunch of stuff here, which is stuff we do that seems to work. And then we've got another bunch of books which talk about how it works. All right? And as I said, we've got all these advances, continuous delivery, we're using the cloud, we're using self-service infrastructure, we've got the techniques from these different books. We've shifted left on testing, on security, on audit, on compliance, on policy, which brings me to the next book. It's not all books, but brings me to the next book. And one of my curiosities, which is, are we real engineers now? So Dave Farley wrote this during lockdown. He'd been doing some talks about it beforehand, where he's sort of making the case that, unlike previously, where we would do a bunch of just random things and it wasn't repeatable when we were building software, with the different techniques that we use now, continuous delivery, test-driven development, the stuff from extreme programming, standardized more or less way of approaching requirements in user stories, acceptance test-driven development, et cetera, build pipelines, shifting left. We've got a repeatable set of tools that we use every single time we approach the idea of building software. And it doesn't matter which domain you're in, it doesn't matter which industry, it doesn't matter if it's embedded software or if it's hard or soft real-time. We've got the same set of tools that we can apply every time. Because this has been videoed, and I don't want to start wars out there, I'm going to sit firmly on the fence and say I'm not sure if we are real engineers yet, but Dave certainly makes a very compelling case for that. Now, back onto flow. Now, work flows as information through value streams, or why shared test environments should be nuked from orbit, because it's the only way to be sure. Now, I mentioned that when we think about how we work, we have someone has an idea or requests a feature, which is a bit of information, right? Someone's head. It's written down, and then it progressively gets turned into more valuable stuff through a series of value-adding activities. In the same way that a set of raw materials eventually turns into a car, right? The raw materials have a certain value. The car, you'd hope, has a lot more value as you go through the set of stages, the value-adding activities that turns raw material into a car. And it's the same with what we do. We've got ideas which have a certain value, but they're only really sort of, when they're in production, when they're earning money for us, they have the most value. So work flows as information through value streams. If you haven't come across value stream mapping before, this is a very simple value stream map, and I really encourage you to actually, if you haven't done this for your own teams, take a look at them. So we've got on this a number of different features. We've got value creating, value adding time, or cycle time. In this case, we've got 3 days worth of software development at the start, a day and a half of testing, and then half a day of deployment. We've then got wait time in between the value-adding stages. This is how long it's taken after you've committed, after those 3 days, until it's picked up for testing. In this client of ours, it was on average 10 days. You'd have basically committed code sitting around waiting for tests to be, for testing to be completed, or started even. And then once the code was tested, that would sit around waiting for 30 days on average before it was deployed. Right, that's the wait time. And then the whole thing is what's called production lead time. So this is production lead time is from, in this case, work hitting the development team to being deployed. And as you can see, there's some rough figures on here. The production lead time overall was 47 days, and the total value-adding time was only 5 days of that. So you've got essentially stuff sitting around in queues, waiting to be deployed, waiting to be tested, and so on, for 42 days doing nothing. Now, this comes on to one of Don Reinhardson's most famous aphorisms, which is around the problem with what we do is that our work is invisible. Right? We can't see the inventory that sits building up in front of us. As developers, as testers, we might see maybe some stuff in Jira, big long list in Jira. But it's not the same as in manufacturing, where if you've got a machine and there's a whole bunch of raw material building up and building up and building up in front of it, you know you've got stuff sitting around and it's a problem. Right? It's very hard for us as knowledge workers, doing what we do as technologists, to understand the entirety of where the work is sitting within our flow. Because, we're concentrating on doing our thing. We're writing code, we're committing, we're picking up the next user story, writing test code, committing, etc., etc. Right? We're just stuck in our own little cycles, usually. And we don't often either look across the whole system of work, and we certainly, or usually, don't look all the way up to where ideas come from. We might have a site of deployment and testing, but not necessarily on the business process that generate feature requests or so on. So this is, as I say, a real value stream map that we made for a client. This is a more, usual sort of looking one. This is for a company that was about 150 or so, a bit older than that, years old. I've shown this before in other talks. I'm going to drill into a few features of this. So, first off, I should point out, so at this end, we've got a bunch of really smart people working really hard. They're like enterprise architects and that kind of stuff, and business folk generating ideas. Down that end, we've got a bunch of people testing stuff. In the middle, we've got some data people doing data stuff, and then, I'm not sure if this is going to work, but there's one of the little blue post-it notes in the middle, that's writing code. And the whole length of this was probably about 18 months to 2 years. So when they were sort of coming up with ideas, they wouldn't be expected to see those ideas actually in production or generating value for them for about 2 years. And yes, they were very frustrated by this. On this, you've got a number of different features. And it's a number of different types of reason that teams sit around waiting for stuff, or people sit around waiting for things. It's essentially, block is in the way of flow. The first is coordination. And coordination is when you've got two or when you as a team or as an individual are waiting on two or more other teams to get stuff done before you can start. So maybe it's a big program of work. Maybe one team has to provide you an interface, another team has to provide you with some database schema or something, and you can't get your stuff done until those teams have finished. So this is an example of this. In this case, the developers will have to wait on two different types of data team to coordinate changes before they could start. The next type of wait time is scheduling. So scheduling is when you're waiting on a cadence, you're waiting on a meeting. Maybe it's a change request with architecture review board. And in this, again, there was a whole ton of change request boards and architecture review boards going on. I did mention this fact earlier, but change request boards actually predict low performance. And then the third type of wait time is stuff sitting around in queues waiting to be done, waiting to be picked up and worked on. And of course, the deeper the queue, the longer it's going to take from the thing to get from the bottom to the top. And sometimes you have got lots of these queues. Sometimes you actually have all three of these different types of wait times all at once. And this is why we should nuke shared test environments from orbit, because often shared test environments exhibit all three of these wait times. So, you're waiting on maybe other versions of software to be deployed before you can deploy into a test environment. Maybe there's a queue that you have to of other teams that are before you, or maybe you have to schedule 6 weeks in the future to get in for a particular release. Now, this is one of the things that freaks me out when often the reason I get given for why we've got shared test environments is because they're too expensive to get another one. We've got only one instance of this thing, whether it's SAP or it's whatever it is. So we can't have another one because it would cost us 30 grand. But of course, if you've got 10 teams all sitting around waiting and blocked, it doesn't take long before you've already spent more than 30 grand on just people sitting around doing nothing. Quick sidebar now on generative science, because I'm going to be using some modeling techniques to show you some techniques for improving flow. So generative science is it's this idea that you create models and simulations of the real world, simplified versions of the real world, and then you use those models and simulations to test out ideas about how the world works, fundamentally. So this is a very simple version of an agent-based model. This is implemented in NetLogo. If you've ever come across Logo, this is the multi-turtle version of Logo. And in this, what we can see is the flocking behavior of birds. Or rather, we can't, because they're not exhibiting that behavior at the moment. So with generative science, what you do is you set up a simulation with a set of parameters, and then you tune the parameters to see if interesting things happen. In this case, we've got how close these agents can get to one another, how quickly they can turn, and how far they can see ahead. And with this configuration, you get this chaotic or Brownian motion. But if you change those parameters very simply, the system undergoes a phase transition, and you suddenly start to get this interesting behavior that you can use to ask questions of. So in this case, they start to form these pretty flocking patterns, like starlings and memorations of starlings. I mean, you can do much more interesting stuff with this. This is a model you can run which shows the spread of viruses, essentially dependent on how close you get to one another, these agents get to one another, reinfection rates, immunity rates, and so on. And of course, this is a toy version, but these models were used during the COVID pandemic globally to try and understand the effect of the different rules that were being imposed in different societies. And I know that because ThoughtWorks was responsible for implementing a large-scale model in Rust. This is the framework EpiRust. And this was used to build something called Bharat Sim, which modeled the spread of COVID in Mumbai. So, this is tens of millions of people modeled as agents, and you could ask questions if you get too close to one another. Is it 1 meter, 2 meters? The effect of masks, the effect of different group sizes, and so on. So, they can be used to do super interesting stuff. You can also do things like model economics and the exchange of value. So this is a little graph that shows, using agent-based models, this brilliant paper, that you can create the Gini coefficient using agent-based models. That's the proportion between rich and poor. I'm not sure if Poland's on here. But essentially what this agent-based model shows when you run it is that unless you have market controls, every single capitalist society will end up as an oligarchy. And the level of market controls that you have, that will basically end up whether you're in a no oligarchical state or a partial oligarchy. And you can get the Western state, well, some of the Western countries' Gini coefficients out. So these are kind of interesting things, and you can use these to do interesting things. But back to following the work, or why traveling slower makes you go faster, and why queuing for lunch at conferences sucks. Sorry, conference organizers. Because you can use these agent-based models to model flow, and you can sort of use them to play around with different ideas for improving flow. So, for example, From principles of product development flow, we have this idea of congestion collapse. When loading becomes too high, we will see a sudden and catastrophic drop in output. Now, this affects us on our teams, right? So when we've got too much stuff going on, we're working super, super hard, right? Everyone's like flat out, 100% utilized, like super, super busy, but nothing seems to be happening. We don't seem to be producing anything. Maybe we're context switching, maybe our bosses are getting annoyed, so they're adding new requirements and preempting work in the queue, but we're working super hard and nothing seems to be happening. And this is an example of a system that's undergoing congestion collapse. And you can model this very simply like a highway. So, if you've ever been on like a motorway or whatever, or a busy road, and there's no crash or anything like that, but all the cars start bunching up, and then bunching up and expanding, bunching up and expanding. That's because the system of the highway is undergoing congestion collapse. There are too many cars on the road for that speed. You will always get this phase transition for the number of cars and the speed they're going at. You will always get the transition towards congestion collapse. There's nothing you can do about it. There's just too many cars on the road. It's the same in our teams. Right? There's nothing we can do to avoid congestion collapse if we've got too much stuff going on. Our teams will undergo congestion collapse. But you can make some changes. Right? This is one of the things you can do, control occupancy to sustain high throughput in systems that are prone to congestion, like the teams we work on, or like highways. On highways, what you can do, and this is another run of this simulation, and the only thing I've changed is the number of cars. They're going at the same speed, same acceleration, deceleration rate, but because you reduce the number of cars on the highway, it doesn't undergo congestion collapse. And we can do the same thing on our teams. This is why work in process limits are so interesting. Right? Using work in process limits in our teams helps us to avoid congestion collapse. Helps us to avoid taking too much stuff on and the context switching and reprioritization that happens when you do that. This is another example from principles of product development flow. The second queue size control principle. Don't control cycle time, control queue size. So this is the question, how long at a conference do you have to wait for lunch? I go to a lot of conferences. There are some that do way better than others. Actually, Devoxx is actually pretty good for reasons I'll come to in a moment. But how long do you have to wait? So if you have this kind of like timeline, lunch is served at 1, etc., and then you've got the rate of people arriving at lunch on the y-axis. So lunch is served. And maybe there's a bunch of exhibitors who start eating lunch. This is this constant rate of arrivals. And then suddenly the session's finished and tons of people all turn up for lunch, right? All these people suddenly turn up and start queuing, essentially, at the lunch tables. This is why this is pretty good, because there's lots of lunch tables to queue at, right? If you've only got one, can you imagine the queue size for 2,000 people? And then you've got people, once they've queued, they've got their food, they can wander off and eat their lunch. The problem is the system of serving lunch has only got a certain capacity, right? Those tables can only support a constant rate of people arriving and leaving, or within bounds. Now, if you wait until someone's queued up for ages, right, and then ask them, how was your experience, right, so the session's finished there, then you're gonna have to wait a long time to understand that you've got a problem in your system. Because it's going to take them a long time to progress through that queue. It's a trailing indicator of performance, essentially. And that's why, interestingly, things like velocity or cycle time, these are trailing indicators. They can only tell us after we've had a problem that we had a problem in the past. But in fact, if you just measure how deep the queue is, we know immediately if we've got a problem. And this is what supermarkets do. They have like video cameras pointing at the tills. And so they can see, as the queues build at the tills, they can call more people to go and work at the tills. Right, so looking at the queue depth, the amount of work in your backlog is a much better indicator of is a leading indicator of how long things will take. And in fact, there is a relationship called Little's Law between them. So the batch size queuing principle, that's the next one. Reducing batch size reduces cycle time. Continuous delivery. Single piece flow, working in small chunks and pushing them all the way through our software development lifecycle until they're in production, as opposed to waterfall, which is, kind of everything has to be defined, then everything analyzed, then everything developed, then everything tested, then everything deployed. Because there's a relationship essentially between batch size, queue depth, and cycle time. Essentially, on this graph, what we've got is two big batches being worked on, then deployed, worked on, then deployed. And after a period of time here in the middle, those changes are going to start earning money. If you make no change at all, same work, same period of time, but just deploy more frequently, you earn a giant amount more value, because you start earning value for the first chunk there, for the second chunk there, third chunk there, and the cumulative effect of all that value over time is enormous. In fact, Don Reinhartson goes on to say, batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization, without adding people or making them work harder. Just by deploying more frequently, if you deploy twice as often, you've doubled throughput. I mean, who wouldn't want to be able to say that to your boss, to their boss? The next principle I'm going to talk to is the principle of face-to-face communication. Exploit the speed and bandwidth of face-to-face communication. Now, I know this is somewhat controversial these days in a world of hybrid working and so on. And yes, you can work very effectively in a hybrid or remote first way, or even remote only way. But the bandwidth of communication is much less. And actually, the highest bandwidth is when you're face-to-face. I'll give you an example of that. So this is an event I was at in Anguilla in the Caribbean. Someone's got to go to the Caribbean to events, so that's me. This is me. This is Adrian Cockcroft, Netflix, ex-Amazon, in the middle. And then this is Melvin Conway. He's actually real. Melvin Conway of Conway's Law fame is a real person. He still exists. He's doing some very interesting work at the moment, in fact. And we were talking at this conference about the uses to which we put Mel's work over the years. And Adrian was explaining at Netflix how they would organize the team so that the people who need to speak to each other the most sit close to one another. So if you're developing the UI for the televisions or whatever, and you need to call the platform APIs, and then the platform APIs then call the services behind them, you sit those people next to the platform team. Platform API team. And they're nowhere near the Cassandra admins who sit miles away at the other end of the building, because they don't need to talk to them very often. That's why you should never sit next to the Cassandra admins unless you're the network engineers, I suppose. So this idea of face-to-face communication, optimizing for bandwidth, optimizing for sitting people close together if you want to go fast. There's another piece of advice which I really love from L. David Marquette in this brilliant book, Turn the Ship Around about leadership, where he says, again, don't move information to authority, move authority to the information. So create teams where you allow them to move independently, autonomously forward together. Again, improving flow. If the team's got all the information they need to make a decision themselves, then that's going to be faster than them having to ask other people. So, back to modeling flow, using generative science to model flow. So I showed you this value stream earlier, and I had it in my head, this idea that you could actually take these value streams and turn them into living things, rather than have them as a static thing, which is you model the process once. Actually turn these into living things. And you could do that, again, using generative science. You can create little agent-based models of the value streams in which we work, of the systems of work in which we work. And so, we did some thinking, me and a few of my colleagues, and we thought about what are the things that people are doing in these value streams. So we have this idea of an enterprise architect machine. It's a bit reductive. We're all machines in my brain now. So the enterprise architect machine, and what they do in this case is they take business requirements documents and solution designs, or they sit on the enterprise architecture says no committee, and they do some stuff and they turn it into other things, which is kind of, if you think about it, mostly what we do. We have an inbox and we have an outbox. If I'm a software developer, I might take some code from the inbox, take a user story from the inbox, write some code, and then I've got committed code in my outbox. If I'm a tester, I might pick that up and test it and so on. But essentially, that's kind of the world in which we work. This is this idea from Charlie Stross of executing the organization's algorithms very, very slowly. The organization's processes are the algorithms, if you like, and we're in them as machines executing them. And you can start to model things like the different types of wait time and so on. You can model things like synchronization, you can model scheduling, you can certainly model queuing pretty straightforwardly. You can model things like interrupts. So, if someone wants you to do a piece of work more urgently, you can interrupt tasks and so on. And you can implement all that using pretty straightforward, these days you might even think about using an LLM to do this, but you can implement this using techniques from gaming, from game development. So this is something called, or a depiction of something called the behavior tree, which lots of NPCs in computer games use to take decisions autonomously. So it's essentially a finite state machine in graph format, as opposed to like in object mode, if you like. So you can implement that as maybe some C# code, which is this. This is the default behavior for a developer. The developers do stuff in my model. And then you can put it all together and you can see what happens by running simulations of the world of work, of how we work and the flow of work through the systems in which we work. And when you run that model, this is based on a waterfall team, 100% batches, and an agile team, single piece flow. You can get some interesting results, or the results you'd expect, probably. In this case, you can see that the waterfall team are all blocked, waiting for ages, and then the agile team is deploying software. And what you end up with is graphs that look like this, where the agile team, and independent of team size, team shape, and so on, you always get graphs that look like this, dependent on batch size. The red line is the cumulative value delivered by the agile team, and the blue line on the left-hand side is the cumulative value delivered by the waterfall team, and then the lead time on the right as you're looking at it. And you can see, obviously, the agile team has delivered a huge amount more value, which we would expect because we've all read the principles of product development flow, have internalized it, and deeply understand the economics of software development, right? But it's an interesting result that you can model how our teams work using these techniques. And by the way, we're in ongoing development of this, so there's more to come. Artificial general intelligence is already here. We call them companies, and we get paid to execute their algorithms very slowly. I'm not suggesting you can model actually humans like this, but you can model them in enough detail that you can get interesting results. So, how flow works. I just showed you sort of the curious domain model of how we work, going through these series of value-adding steps, producing stuff that has more value from stuff that has less value. I showed you these sort of 6 books ages ago that I sort of think are the sort of foundations of optimizing the way we work for flow, for the fast delivery of and safe delivery of value. But then, this stuff we do that sort of empirically seems to work, this is the sort of reason it works, or the how it works, the economics, the science, etc. Then I think all of this is based on a bunch of other interesting stuff called complexity science. All of this is based on these sort of foundational books. So Scale and the research behind it, Quark and the Jaguar, complexity, etc. Okay. So I promised you some curiosities. How did I do? So the surprisingly recent invention of all the things, I think we covered off that. There's a bunch of stuff that we take for granted now that are less than 10 years old, which is kind of crazy. Why AWS and self-service ate your lunch? Well, it's the self-service part, basically. If you're building platforms, make sure that you're building platforms that offer self-service. Right? Don't impede the flow of work by putting people or other things in the way. Are we engineers now? Well, I'm on the fence on that still, but we're getting there. Phase transitions in oligarchic societies, unless you put market controls in, all societies, or capitalist societies will end up as an oligarchy. So, just a thought. Why traveling slower makes you go faster? Well, I showed you that example of how if we put things like working process limits in place, we can avoid our teams going into congestion collapse. Right, that's an example of that. Why you should never sit next to the Cassandra admins? Well, unless you're the network engineers, but if you're the UX people, you probably don't need to. And what Lego has learned about batches? Haven't covered that. Remember I mentioned this, batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. Now, I'm a father, but I'm also, so I've built a lot of Lego with my kids over the years, but I'm also an adult fan of Lego, so I build Lego myself. And I've noticed, that's technically a thing, adult fan of Lego, just so you know, I didn't make that up. And so what I've noticed over the years, you probably have as well, if you've been building Lego for a long time, is they changed how they package it. So what it used to be is a bunch of bags with a bunch of random bricks in, and then this big, instruction guide, instruction manual. They don't do that anymore. What they do now is they package up, right, a set of pages in the manual into a series of numbered bags. Right? Because if you were Lego and you wanted to make the experience of building the sets more fun, more enjoyable, and faster, what would you do? And what Lego would do is reduce batch sizes. That's the simplest thing you can do to go faster. If you halve your batch size, you double your throughput. And that's all I've got. Thank you very much.